Welcome to the Henry AI Labs walkthrough of Keras code examples. Keras has provided 56 code examples implementing popular ideas in deep learning. This ranges from the basics such as simple MNIST and IMDb text classification, all the way to cutting-edge research ideas such as knowledge distillation, supervised contrastive learning, and transformers. We'll also explore fun, generative examples like variational autoencoders and CycleGAN. My contribution to these code examples is to explain every single line of code in each of them, walking through each of the individual Keras examples. I'm not the author of these code examples. Please consider starring the GitHub repositories to show support to the original authors. The next Keras code example is point cloud classification with PointNet. Point clouds are these three-dimensional point sets that are basically like voxels, except for the way that they're manifested as just points. So differently from our previous Keras example with 3D image classification from CT scans, in this example we have this three-dimensional volume where we have height, width, and depth, and then in each slot we have a voxel, which is like a different kind of pixel that represents each individual point in this three-dimensional cube. A point cloud is different from that in the sense that it's just going to have an X, Y, Z point, and that's all we use to identify it in this three-dimensional space. So here are some more resources if you want to learn more about point clouds more generally. It's a really exciting area of computer vision and computer graphics and things like the LiDAR scans that help with autonomous vehicles. So I find this useful, this Wikipedia page. Also, I found this on 3D printing, Stack Exchange, a quick description of the difference between raster graphics and then vector graphics, and you see the pixels, voxels compared to this idea of point clouds, and then these things like triangle meshes, which we'll get into also. And then this is Geeks for Geeks, talking more about vector-verse raster graphics and a little more details about this. But for our sake, what's most important to understand is that we're going to be representing each point in our three-dimensional space just as an X, Y, Z coordinate space. So finally, before getting into it, if this tutorial inspires your interest into these three-dimensional meshes, point clouds, and this kind of geometric deep learning and computer graphics, I highly recommend checking out this PyTorch geometric library. It has documentation with these basic introductions all the way up to more advanced things, different data sets you can use, different neural network layers that have been implemented, and data augmentation functions. This is a really exciting library, the PyTorch geometric, and so maybe this tutorial will help you develop an interest for this as well. The first step in our notebook is to install the TriMesh library. Basically what's happening with this TriMesh library is it's drawing triangular meshes using our XYZ point cloud coordinates. So we can just sample this and just plot them on the three-dimensional grid with our sample of XYZ coordinates, but what's common to use in computer graphics is to draw these triangles, and I don't know too much about exactly how this happens, but it looks like what you do is you draw these polygons that connect the point clouds, and that's one strategy of rendering and visualizing these three-dimensional objects that are stored as these XYZ coordinate data structures. So then we have our pretty standard imports, our operating system, glob for aggregating these file paths, the TriMesh library that we just discussed, NumPy, TensorFlow, Keras layers, and Matplotlib, and then we're going to set our random seed. So the next thing to do is to download the ModelNet 10 dataset. The ModelNet dataset, maintained by Princeton University, is a very interesting effort for maintaining these 3D deep learning datasets. So as shown in the top, we have over 125,000 CAD models labeled into 662 object categories, and then it also describes that we have 10 categories with annotated orientation. So I'm not exactly sure what that means. It must have something to do with the XYZ three-dimensional space. So in the beginning of this ModelNet project page, they describe how they constructed this dataset, how they used Mechanical Turk to label the CAD models, how they derive which objects to construct CAD models for with the Sun database, and so on. So what we have is we have this data set, we have these different benchmarks of classifying these objects, and in a second in our Keras notebook you'll see exactly what these look like. So each of our point cloud objects are stored in these .off mesh files as downloaded from this link with our ModelNet 10 data set. So we use the TriMesh library to load this, and it's going to draw these polygons that connect the point clouds and render this mesh. So we see how we can rotate this around with our mouse, and this is really interesting. This is really different from the two-dimensional data that we classically use with computer vision like ImageNet, CFAR, and so on. So this is really cool. We're seeing this three-dimensional object and how to access it by downloading the ModelNet dataset, and then how to use the TriMesh library to load it and visualize it. The next step is to convert our mesh file to a point cloud file by using a sampling operation. So we're going to randomly sample 2,048 points from this chair object, And then we're going to plot it in 2 dimensions by just indexing the x and the y coordinate in our scatter plot. So we have this visualization of our chair image in 2 dimensions. This is the result of taking 2048 XYZ coordinate samplings from this original mesh object of this chair image. And we have all sorts of other objects as shown later in the presentation. We have things like tables and a dresser, and I think there's even more object categories as stated in the Model 10 project page. This next function is going to loop through all of the paths for these different objects that we've downloaded with our ModelNet link to getting this data set, and it's going to loop through them, load them with the trimesh library, and then sample the 2048 points that are the XYZ point cloud points that are going to represent each object. So then we convert these points into a NumPy array. We have our train points, our test points, our train labels. We're going to be classifying these into object categories similar to like ImageNet, but with these 3-dimensional objects. And then we return this data set that's going to be pipelined into our tf.data.dataset object. So this is actually calling that function parse dataset, and here we see the different 3-dimensional classes that we have. We have a bathtub, sofa, dresser, desk, table, nightstand, monitor, bed, toilet, and chair. So we have these different kind of like objects that you would see in a room or something like that, and we're classifying them into these object categories based on their 3-dimensional coordinates. So definitely a really cool idea of deep learning. So next we're going to actually apply data augmentation as well to point cloud data. And the particular data augmentation that's used here is jittering the points. So the points are randomly sampled on this mesh surface. So an interesting and a natural data augmentation would be to jitter them around and add this random noise to their position in the XYZ space. So that's what we're doing. We're using this jittering, and then we have also tf.random.shuffle the points, where we're randomly shuffling how they're presented sequentially with respect to this data type of 2048 XYZ pair. So we're shuffling them so that the model isn't biased towards any particular ordering. There could be the way that it's doing this sample function, the way that it's sampling these 2048 points, it could be that there's some high frequency pattern with the way that this function is actually implemented, and we don't want that to bias the solution of our model. So we implement this shuffling as well with the points. So we have this random noise style jittering, and then we have this shuffling to make it so we can augment our data set and then prevent overfitting in the data space. So then we convert these data types to our tf.data object by using the from tensor slices call, passing in our training points. These are these 2048 XYZ pairs for each instance, and then our labels of the object categories such as bathtub, sofa, dresser, and so on. So finally we have our data set. We chain in our augmentation function by chaining on .map, augment, and then .batch. Batch size is the syntax for using these tf.data.dataset objects in Keras. So now that we've prepared our data set with our input outputs for deep learning, let's look at the model architecture itself. So I think it helps to jump ahead and look at the model.summary. So our input data is 2048 points, each with an XYZ coordinate. So therefore our input shape is 2048 by 3, because we have 2048 points, each one has XYZ value. So that's our input layer, and we're going to originally convolve over that with a one-dimensional convolution. So a one-dimensional convolution, different from, say, the classic two-dimensional convolutional kernel, is instead of using like an n by n kernel, we just use n by 1, a single-dimensional kernel. So we're going to pass this kernel along through the image, convolving it and blowing up the feature space, so we go from 2048 by 3 to 2048 by 32. This Keras code example replicates the architecture described in PointNet, deep learning on point sets for 3D classification and segmentation. So what I took away from this is the high-level idea is that it uses these TNet blocks to kind of move these 2048 by 3 point cloud points into kind of a more regular space for sequential processing of deep learning architectures, similar to like pixel grids or any kind of data structure. So this is done by having these nested TNet blocks. And so the TNet, it has this way of taking these input space of the 2048 point clouds and then projecting it into like a matrix that we can use for a more standard deep neural network pipeline. So the key to this is this orthogonal regularization shown here. So the high level the equation is just that the regularization is that the identity matrix minus this feature space matrix by itself transpose should be minimized. And by doing that, they reason about how they say that helps with the alignment of the feature projection and so on and so on. But I think it's a little hand wavy. It's kind of it's maybe a little. It's just kind of like, in my opinion, just these feature transformation ideas, and I don't think there's too much intuitive reasoning behind it, in my opinion. But I don't know too much about this. But the idea is that you have these TNet that are projecting these point cloud representations into these matrices, where we then apply standard things like once we project this, then we're just going to kind of stack these layers of convolution and batch normalization, ReLU activation. So the TNet is the way of projecting these point cloud representations into a more normal feature space for deep learning. So I know that wasn't the best explanation. If you're curious about the exact intuition behind the point net architecture, I highly recommend just reading the paper. But we're going to kind of try to understand this by seeing what's been implemented in Keras. So the next step is they construct these convolution batch norm activation layers. This is a pretty standard block in deep learning. And now we're getting into the meat of it. This is the TNet block. So as stated in this documentation, the TNet is the way that you do an affine transformation matrix by its own mini network, transforming these point cloud set of 2048 XYZ inputs into a canonical representation. So affine transformation is going to preserve the collinearity of these points and project it into kind of a more standard matrix feature space that we're used to seeing in deep learning. And so here are the actual details of how they construct this TNet. They have this orthogonal regularizer, which is going to try to push the distance between the features, and then the features transposed, subtracted by an identity matrix, which is just a matrix that has ones along the diagonals and zero everywhere else. This is just the regularization technique that's going to be, I don't know the exact motivation behind this kind of operation, but I imagine it's trying to keep the diagonal dimensions orthogonal distance from each other with the way that you transpose the matrix and multiply them together, and then subtract the identity matrix along the diagonal, so that you have these different dimensions of the matrix. So obviously there's more linear algebra behind that, and that's a horrible summary of it. But so here's the actual implementation in Keras that gives us a more tangible sense of what's being done here. So we have our orthogonal regularizer, where we have the number of features, the L2 regularization, which is where you just square the distance and then take the square root of the sum of that. And then we have our identity matrix. So we're going to reshape our intermediate features so they're compatible with this matrix multiplication, where you multiply the intermediate features by itself transposed. And then you're going to do the reduce sum, where you have this operation of multiplying the L2 regularization, which is where you're doing that squared and then the square root of all that, and then by the distance between this transpose and itself multiplication minus the identity matrix. So this is how we're going to be regularizing these intermediate features. And then we see how this is all compiled into the TNet block. So we start off by having our bias parameter, this constant, another identity matrix with a number of features, then it's flattened into a vector. And then we have our orthogonal regularizer, which we see is into our dense layer as we're projecting this into the final number of features. So we stack together these blocks. We have a max pooling where we're reducing the dimensionality. It's kind of like just template stuff as we add these sequential processing layers. And then we reshape it into, say, 2048 by 2048, this matrix. And then we do this dot product between the inputs and then the features that were constructed from our TNet. So we do kind of have this like skip connection operation with these transformations. So, it's a bit complicated, and I'm not sure exactly what's going on here, but, here's the high level overview. And, if you're interested in this further, I recommend checking it out and going deeper than this quick tutorial. Okay, so that was a bit of a fail with trying to understand these TNet blocks. Maybe we'll see how it all comes together and it'll make sense then. So we construct our architecture by just repeating these blocks together: x equals TNet, the conv batch norm activation blocks, and then another TNet block, and then finally we have a max pooling, dense layers, and then mapped into our classification layer. So now we see the model in Keras model.summary. So the input layer, we understand that's the 2048 point clouds, each with an XYZ coordinate. And now we have our first TNet block. So this first stack of operations that ends with this dot product, it returns 2048 by 3 as a result of our TNet block. So this is the output. As we saw, the last dot product, it's layers.dot. This is the last thing we're going to do in our TNet block. So we see that in our TNet block, we have this blow up of the features where we just use a one-dimensional convolution that goes from 2048 by 3 to 2048 by 32, batch norm activation, another stack of that, as we saw as we're repeating that in our architecture. And then we have, so this dense layer here and here is where we applied this, is where we're applying this orthogonal regularization, or not actually the first two, the last one, where we're projecting it into the largest space. So let's see where that was. So that is the one. So that is this, no, that's this dense layer 9. So the number of features is actually the 3 by 3, referring to the XYZ coordinates. So the number of features, this parameter of our regularization in our TNet blocks, is about the XYZ points, not the 2048 sampled points. So we end up with this 9, then we reshape it to 3 by 3, dot product with the original 2048 as we skipped ahead this original representation. So overall, it's, in my understanding, it's kind of like a black box set of operations, but you can check out this paper if you want to really understand why they're aggregating these transformations in this way. And I'm sorry I didn't quite have the interest to really dive into this, but here it's somewhere in this paper if you really want to mine through it and figure out the motivation behind why why exactly they're stacking these operations like this, and their motivation behind projecting this from 2048 back into 2048 by 3, and the motivation behind these intermediate operations. So that was our model, and it's a bit complicated and I don't completely understand it, but finally we're putting it together and we're back to the familiar territory of our Keras modeling, because at the end of the day we have our input-output space. We're just fitting these labels with these point cloud coordinates, and we have some model, some way of transforming from this original 2048, a sequence of these layers, and then finally we have the output 10 classes for predicting 10 class classification. So we use our sparse categorical cross entropy loss function, we have an atom optimizer, and now we're just fitting the data with model.fit, 20 epochs taking about 10 seconds per epoch. We see the loss monotonically decreasing, and our accuracy is pretty good, about 80%, at modeling these object categories from these three-dimensional point clouds, which is a really exciting result, really high accuracy for modeling this with about 700,000 parameters and only 20 epochs through the data. And it does look like if you train this for further, it would do even better at modeling the training data. And then we do see that the validation set accuracy is decreasing as well, although it's more jumping around. We see how it jumps from 76% here back to 70 and so on, but it does seem like it hasn't overfitted quite yet. So finally we have a trained model and we want to visualize some of its predictions on the test set. So we do this with our tf.data.dataset object.take is how we sample the next batch of data. Then we're going to index it to take the first 8 points, which we're going to visualize, and then we're going to run them through the forward pass of our model, and then we're going to take the argmax, which is the, we have this softmax distribution of the predictions, and the argmax is the most probability density that the prediction had put on any given class label, like table, sofa, desk, and so on. So we have the points equals points.numpy. We convert it into a numpy array from our, I think we originally have a trimesh object. Let's go back to this data loader. Okay, so I'm not sure exactly why they need to convert it again to a numpy object. I think it already is that. But now what we're doing is we're just plotting the x, y points of each of these individual point cloud objects, and then also titling them with the ground truth label and what they had been predicted. So we see how our model is pretty good at predicting these things: table, table, bed, bed, chair, chair, and so on. So overall, that's our presentation on point cloud classification in Keras code examples. So to summarize all this, I hope this was a decent introduction to point cloud classification, and I hope I didn't mess up walking through this Keras code example too much. Mostly I was pretty confused by this point net architecture and trying to understand exactly what's going on with this TNet transformation and how they're using this orthogonal regularization thing, showing the identity matrix minus the feature matrix transpose. Exactly why that's used and the motivation behind it, I wasn't so sure of that, but I think from this Keras code example, we're able to at least have a sense of how to load these point cloud objects, these triangular meshes, this library, and how we have this file path of these ModelNet 10 dataset, and you can see the project page, which will be linked in the description of this video as well. And then, we can really just treat this as a regardless of this point net architecture, which was a bit confusing, we can just treat this as any mapping of inputs from 2048 by 3 into these 10 object categories. So how you do these intermediate processing, is up to you. And I think like maybe a transformer layer for this unordered set of point clouds, something like that could be interesting. I don't think this is the only way of doing it. And then we also saw this data augmentation, which I think is interesting, this jittering and then the shuffling of the points to make it have this permutation and variance in the data space with data augmentation. And then overall we saw just, with this architecture fitting it and how it performs really well in only 20 epochs. We get 80% training set modeling accuracy, 77% on the validation set. And then when we visualize our predictions, they look correct. And then, so also this is just the syntax if you want to take this apart for how you sample this point cloud representation, then just plot the XY points in this two-dimensional plane in Matplotlib. So overall, I hope this is a decent introduction to point cloud classification and inspires your interest further. And again, if you're interested in this, I highly recommend the next step would be checking this out. And me personally, I have never done this in my life before. This is my first time actually looking at a one of these point cloud or even a voxel. I've seen this. We've previously looked through this three-dimensional image classification where you do have this volumetric object and you use the three-dimensional convolution. But I think that's really different from the way that data is represented in point clouds. And again, if you're curious, this blog post from Geeks for Geeks describes vector versus raster graphics, and I think that further communicates this difference between point clouds and then like voxel representations and 3D volumes. So thanks for watching, and please check out the rest of the Keras code example series on Henry AI Labs.